The topic for today is Green's theorem. Green's theorem is a major result in the calculation of line integrals in 2D, and it's comparable with the fundamental theorem of calculus in single variable calculus. It's really foundational. And what it does is it tells you that we can calculate a line integral around the boundary of some kind of region inside two-dimensional space by calculating a double integral on the inside. And it has a physical interpretation too that we'll get to in a minute. As a formula, it says, suppose we've got some region in 2D, let's call it R, and its boundary is some curve, C, that's oriented counterclockwise. So for example, if we've got a circle here, then a counterclockwise orientation around its boundary is what you think it is. We've got something like a square, then we just kind of consistently move around the outside boundary in a square, around the outside of the boundary of the square in a counterclockwise direction as well. And we'll talk a little bit about this orientation in another part of this lecture material today. What Green's theorem says is that if we calculate the line integral of a vector field around the outside boundary, that's the same as calculating the double integral of the curl. So it calculates the double integral of the curl of f with respect to area over the inside of the region. Here, curl means scalar curl. As a formula, if we use this alternative notation, the line integral of p dx plus q dy around the outside boundary is the same as the double integral of del q del x minus del p del y over the inside of the region. So that's very, very handy. It converts between integrals on the outside boundary with integrals on the inside, and it gives us a formula for how to relate the thing we should be integrating for the line integral to the thing we should be integrating for the double integral. In a physical interpretation, we talked about how line integrals can be thought of as measuring circulation. If we've got some fluid flow, then at each point the fluid is going to be pushing a line integral around the outside boundary. What it does is it says, okay, let's see how much the fluid is rotating in a direction that's parallel to this outside boundary. And what the Green's theorem says is that instead of doing that calculation, instead of figuring out the total amount of rotation around the outside boundary, what we could do is we could look at the curl. And what the curl tells us is the curl tells us how fast the fluid is rotating at each point on the inside of the region. And if we add all of those up, it gives us kind of a total amount of rotation for the whole region, full stop. So that's one way to think about Green's theorem physically.